Hello, in this lecture we'll answer on two questions. In the first question, we find out the area of this green shape that is inside square ABCD. And in the second question, we'll find out the area of this green shape that is inside quarter circle AOB. So we'll start with the first question. In the drawing we have square ABCD. You know that line segment PQ equals to 2 units in its length, line segment CQ equals to 3 units in its length. This is angle PQC, that is a right angle. Again, our mission is to find out the area of this green shape that is actually quadrilateral PQCD. So first of all, we define one side of this square ABCD as A. So AB equals to BC equals to CD equals to AD equals to A according to our definition. So it is on. This is side AB. That is equals to A units in its length according to our definition. This is side AD. That is also equals to A units in its length. This is side BC, that is also equals to A units. And this is side DC, that is equals to A units. In addition, we know that all the angles inside any square are right angles, so those four angles are all right angles. So write it down. This is a right angle. This is a right angle. This is a right angle. This is also a right angle. In the next step, we define the length of this line segment QB as X. And therefore AQ equals to AB plus QB. So write it down. For the drawing, it is very easy to see that AQ, the missing line segment AQ, equals to AB plus QB. So AQ in total equals to, this is line segment AQ, that equals to AB, that is A according to our definition, minus QB, that is X. So in total, AQ equals to A minus X units in its length. So it is known AQ equals to A minus X. In the next step, we define the size of this angle BCQ as alpha. So in the right angle BCQ, this angle equals to alpha, this angle equals to 90 degrees, therefore this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. AB is one side of square ABCD, therefore it is absolutely a straight line. So if we focus on this side, of the left side of the straight line, if we focus on the right side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AB at point Q? We have this angle that is 90 degrees minus alpha, this angle is 90 degrees, plus this missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles on the left side of the straight line AB at point Q. So this angle must be equal to alpha. In the right angle APQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this front facing angle must be equal to 90 degrees minus alpha. According to the symbol that said that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy this right angle APQ and this right angle QBC in the new page, and we prove that those two right angles are similar to each other according to angle similarity rule. So actually, those are the two right angles APQ and QBC that are coming from the original drawing. So in the next step, we prove that those two right angles are similar to each other according to angle similarity rule. So why those two right angles are similar to each other? First of all, this angle equals to 90 degrees minus alpha, and this angle equals to alpha. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So actually, this is angle AQP. In the right angle APQ, and it is equal to this angle, that's the reference angle BCQ. In the right angle QBC. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually, this is angle QAP. In the right angle APQ, and it is equals to this angle, this is actually angle QBC. In the right angle BQC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle APQ. In the right angle APQ, and this is equals to this angle, this is actually angle BQC. In the right triangle QBC. Repeat again. angle APQ equals to angle BQC. They are both equal to 90 degrees from also, therefore they are equal to each other. So we can prove that all the triangles inside the right triangle, this right triangle APQ correspond equal to all the triangles in the right triangle BQC, therefore those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. So this right triangle APQ is similar. This is the sign of similar to the right triangle QBC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. Side AP in the right triangle APQ over side QB in the right triangle BQC is equal to side AQ in the right triangle APQ over side BC in the right triangle QBC, and it is also equals to side PQ in this right triangle APQ over side QC in the right triangle QBC. I'll repeat again. I should remember that AP over QB equals to AQ over BC, and it is also equals to PQ over QC. AP is the missing side, so we leave it as it is. Over QB, QB is X, so therefore we substitute QB by X, and it is equal to AQ. AQ is A minus X over BC. BC is A, and it is also equal to PQ, that is 2, over QC, that is 3. So in total, according to equation 1, we should find out that AP over X equals to A minus X over A equals to 2/3. So actually, those two expressions are equal to each other, therefore we get equation 1 from those two expressions that are equal to each other. So AP over X equals to 2/3. So that's equation 1. AP over X equals to 2/3. Here we'll multiply this equation 1 by X, and finally we get that AP, according to equation 1, AP equals to 2/3 X. According to equation 1, we should find out that AP equals to 2/3 X. Those two expressions are equal to each other, so we get equation 2 from those two expressions that are equal to each other. That is to say, according to equation 2, A minus X over A equals to 2/3. So I'll write it down. According to equation 2, A minus X over A equals to 2/3. So here we'll first multiply this equation 2, and get that according to equation 2, 3 times a minus x equals to 2a. We'll open the brackets on this side of this equation 2, and get that 3a minus 3x equals to 2a. Here we subtract 2a from this equation 2, and we get that 3a minus 2a is a, so a minus 3x equals to 0. Here we add 3x to this equation 2, and finally we get that according to equation 2, a equals to 3x. And again, I should found out that according to equation 2, a equals to 3x. Well, according to equation 1, ap equals to 2/3 x. In the next step, I'll copy the right triangle QBC in the new page, and we'll implement the Pythagoras theorem on this right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. Here by PT is a progression for Pythagoras theorem. Firstly, this is right triangle QBC that they come from the original drawing according to the Pythagoras theorem, and this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. So I write it down, this will be equation 3. According to equation 3, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9, and it is equals to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So in total, we found out that according to equation 3, x squared plus a squared equals to 9. This is according to equation 3, while according to equation 2, I found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we substitute a squared in this equation 3 by 3x squared. We will do it now, and we get it according to equation 3. Nine equals to x squared plus a squared. A squared according to equation 2 is 3x squared. So in total we found out that according to equation 3, 9 equals to x squared plus 3x squared. So according to equation 3, we found out that 9 equals to x squared plus 3x squared. 3x squared equals to 9x squared. So in total we found out that according to equation 3, 9 equals to x squared plus 9x squared. 9x squared plus 9x squared is 10x squared. So in total, according to equation 3, we found out that 9 equals to 10x squared. Here we'll divide this equation by 10, and finally get that according to equation 3, x squared equals to 9 over 10. Here we take a look at all of this equation 3, and finally get that according to equation 3, x equals to the square root of 9, that is 3, over square root of 10. So in total we should find out that according to equation 3, x equals to 3 over square root of 10 units in its length. This is according to equation 3, while according to equation 1, we found out that a equals to 3x. a equals to 3x, so a equals to 3 times x, and x according to equation 3 is 3 over square root of 10. So a equals to 3 times x, that is 3 over square root of 10. So in total we found out that a equals to 3 times 3 is 9 over square root of 10. So we found out that a equals to 9 over square root of 10 units in its length. The only thing that is left to do is to find out the value of AP. According to equation 1, we already found out that AP, according to equation 1, AP equals to 2/3 x. Repeat again, if we found out that according to equation 1, AP equals to 2/3 x, so AP equals to 2/3 x, and x is 3 over square root of 10. So we substitute x by 3 over square root of 10. So in total, we shall find out that AB equals to, here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So in total, we shall find out that AP equals to 2 over square root of 10. AP equals to 2 over square root of 10 units in its length. So actually, this is nice with AP, that is equals to 2 over square root of 10 units in its length. What is the length of PD? From the drawing it is very easy to see that PD equals to AD minus AP. So I write it down, PD equals to AD minus AP. PD equals to AD minus AP. So PD equals to AD, that is A, minus AP, that is 2 over square root of 10. So in total, PD equals to A, that is 9 over square root of 10, minus AP, that is 2 over square root of 10. So in total, we found out that PD equals to 9 over square root of 10 minus 2 over square root of 10, that is actually 7 over square root of 10 units. So here, PD equals to 7 over square root of 10 units in its length. In the next step, we'll join points P and C together by a straight line. By joining points P and C, we created here two right angles. The right angle PDC and this right angle PQC. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape is equal to the area of this right angle PDC plus the area of this right angle PQC. Okay, again, we can find out that the area of the green shape is equal to the area of the green shape is equal to the area of the right triangle PDC plus the area of the right triangle PQC, because of the fact that the green shape, this green shape consists exactly those two right triangles. The area of the green shape must be equal to the sum of those two right triangles. That's to say the area of the green shape must be equal to the area of this right triangle PDC plus the area of this right triangle PQC. So what is the area of the right triangle PDC? The area of the right triangle PDC is equal to the base of the triangle that is PD times the height of the base that is DC over 2. And again, the area of the right triangle PDC equals to the base that is PD times the height that is DC over 2, plus the area of this right triangle PQC. What is the area of the right triangle PQC? The area of the right triangle PQC equals to the base that is PQ times the height that is QC over 2. Repeat again, the area of the right triangle PQC is equal to the base that is PQ times the height that is QC over 2. So in total, the area of the green shape is equal to the area of the right triangle PDC, and the area of the right triangle PDC equals to PD. PD is 7 over square root of 10 times DC. DC is A, and we already found out that A equals to 9 over square root of 10 units in its name. So A is 9 over square root of 10 units divided by 2. So in total, we shall find out that the area of the right triangle PDC is equal to the base of the triangle that is 7 over square root of 2 times the height of the base that is 9 over square root of 10 divided by 2. Again, the base is 7 over square root of 10 times the height that is 9 over square root of 10 divided by 2, plus the area of the right triangle PQC. And the area of the right triangle PQC equals to PQ that is 2 times QC that is 3 divided by 2. So in total, we found out that the area of the right triangle PQC equals to the base that is 2 times the height that is 3 divided by 2. So in total, the area of the right triangle PQC equals to the value of this expression. Here 7 times 9 is 63. Square root of 10 times square root of 10 is 10 divided by 2. So in total, this expression equals to 63 over 10 over 2. So I write it down. This expression in total equals to 63 over 10 over 2. Plus, we have 2 times 3 over 2. 2 over 2 is 1, so we left only with 3. So in total, the area of the right triangle, the area of the green shape equals to 63 over 10 over 2. 63 over 10 over 2 is 63 times 10 times 2 plus 3. So in total, the area of the green shape equals to 63 over 10 times 2 is 20. So it is 63 over 20 plus 3. Here we multiply 3 by 20 and then we divide it by 20 in order to have a common factor with this number, and finally again that the area of the green shape in total equals to 63, and plus 3 times 20 is 60, so this plus 60 divided by 20. So in total, the area of the green shape equals to 63 plus 60 is 123 divided by 20. In terms of numbers, the area of the green shape, 123 over 20 is 615 square units. Repeat again, we actually found out that the area of the green shape that is there that we are looking for in this question, it is equal to either 123 over 20 square units. So in terms of numbers, the area of this green shape is equal to 6.15 square units. So we finish with the first question. In the next step, I will present to you the second question and we'll solve it. This second question, our mission is to find out the area of this green shape that is inside a quarter circle AOB. It is given us the question that arc AP is equal to arc PQ and is equal to arc QB. That is to say, the length of arc AP is equal to the length of arc PQ, and it is also equal to the length of arc QB. So all those three arcs, they are equal to each other in their lengths. AP equals to PQ equals to QB. So in the drawing we have quarter circle AOB, and therefore this angle AOB equals to 90 degrees in size. We also know that OB equals to 5 units. OB is the radius of this circle. So if we know that the radius of the quarter circle is 5. Again, the radius of the quarter circle is 5 units according to what is given as the question. And we also know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. So here we can implement rule 20. So I'll repeat quickly on rule 20. According to rule 20, in front of equal arcs, there are equal central angles. So in the drawing, we have a circle, and we also know that the length of arc AB is equal to the length of arc CQ. Again, we know that arc AB equals to arc AB equals to arc CD. Again, arc AB equals to arc CD in its length. And according to this rule 20, in front of equal arcs, there are equal center angles. So those two arcs, they are equal to each other in their lengths, and therefore in front of those two arcs, we have also equal angles. Those two angles that are defined as center angles, they are located in front of those two equal arcs, and therefore they are equal to each other. That is to say, the center angle alpha equals to center angle beta according to this rule 20. So we can actually implement rule 20 in our drawing. But before that, before we implement rule 20, we'll join points O and P together by straight line, and we'll also join points O and Q together by straight line. Again, it is given us the question that the length of arc AP equals to the length of arc PQ, and it is also equals to the length of arc QB. So in front of those three equal arcs, there are equal center angles. Those three angles, they are all defined as center angles, and therefore, and because of the fact that they are located in front the equal arcs AP equals to PQ equals to QB, it means they must be also equal to each other. So if we define the size of this center angle AOP as X, then according to rule 20, the length of this side triangle POQ must be also equal to x, and the length of this side triangle QOB must be also equal to x, because of the fact that those two side triangles are all located in front of those two equal arcs, and therefore they must be equal to each other. So each side triangle equals to x degrees in its size. From one side, but from the other side, we know that AOB is a quarter circle. And because of the fact that AOB is a quarter circle, it means that angle AOB equals to 90 degrees in its size. It is true in any quarter circle. So angle AOB equals to 90 degrees from one side, but from the other side, we also know that the size of angle AOB is equal to x plus x plus x. And therefore, today we should find out that 3x equals to 90 degrees. So I write it down. 3x equals to 90 degrees. Here we divide this equation by 3, and finally get that the missing angle x is equal to 30 degrees in its size. Okay, this is the missing angle x that is equal to 30 degrees in its size. This is also the missing angle x that is equal to 30 degrees, and this missing angle x equals to 30 degrees in its size. So if you focus on the right triangle MPO, this right triangle MPO, this angle equals to 30 degrees. This angle equals to 90 degrees, according to what is given in the equation, and therefore this missing angle must be equal to 60 degrees in its size. Why? Because according to the rule that the sum of the angles in any triangle is equal to 180 degrees, we get that 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees it is 180 degrees. It is the sum of the angles in any triangle. Likewise, we focus on the right triangle QNO. In this right triangle QNO, this angle equals to 30 degrees plus 30 degrees is 60 degrees. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 30 degrees in its size. According to the sum rule, it said that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy the right triangle MPO and this right triangle NQO in a new page, and we'll prove that those two right triangles can go into each other according to angle side angle rule. So actually, those are the two right triangles MPO and NQO that are going from the original drawing. So in the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to 60 degrees, therefore they are equal to each other. So actually this is angle MPO in the right triangle MPO, and it is equal to this angle. This is actually angle NOQ in the right triangle NQO. They are both equal to 60 degrees, therefore they are equal to each other. In addition, the side PO of the right triangle MPO is equal to side OQ of the right triangle NQO. They are there of the circle, therefore they are equal to each other. Each side is equals to 5 units in length, because you know that the radius of the circle is equal to 5. Again, here we have OQ is the radius of the circle, and OP is also the radius of the circle, and according to what is given as the question, the radius of the circle is 5 units. So OQ equals to OP equals to 5, this is the radius of the circle, is equals to 5 units in its length. So I write it down. OP equals to OQ equals to 5, because of the fact that the radius of the circle is equals to 5 units according to what is given as the question. And finally, those two angles are both equal to 30 degrees, and therefore they are equal to each other. So actually this is angle MOP in the right triangle MPO, and it is equal to this angle. This is actually angle NQO in the right triangle NQO. They are both equal to 30 degrees, and therefore they are equal to each other. So we actually found out that all the three angles, that those two angles and the side that included between those two angles, that is side PO in the right triangle and MPO, are corresponding equal to those two angles, and the side that included between those two angles, that is side QO in the right triangle NQO. And therefore those two right triangles can go into each other according to angle side angle rule. So I write it down. I found out that the right triangle MPO congruent, this is the sign of congruent, to the right triangle NQO according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. Okay? So we conclude that the area of this right triangle MPO is equal to the area of this right triangle NQO. So I write it down. This will be equation 1. Because of the fact that those two right triangles can go into each other, we will derive the area of this right triangle MPO is equal to the area of this right triangle NQO. Repeat again. Because of the fact that those two right triangles can go into each other, we conclude that they have also the same areas. That is to say, the area of the right triangle MPO is equal to the area of the right triangle NQO. But the area of the right triangle MPO consists of quadrilateral MN. P, we define this point as point S. That is the intersection point between NQ and PO. And but again, the area or triangle, the right triangle MPO consists of quadrilateral MPSN and also the right triangle NSO. So we can substitute the area of the right triangle MPO by the area of quadrilateral MPSN and the area of this right triangle NSO. We'll do it now. The right triangle NPO consists of quadrilateral MNSP plus this right triangle NSO. Repeat again. Because of the fact that the right triangle MPO consists of quadrilateral MNSP and the right triangle NSO, it means that the area of the right triangle MPO must be equal to the area of quadrilateral MNSP plus the area of the right triangle NSO. Okay, and it is equal to the area of the right triangle NQO. The area, actually the right triangle NQO consists of this right triangle NSO and also this right triangle OSQ. So it is known. Again, the area of triangle NQO, the right triangle NQO consists of the right triangle NSO and also triangle SQO. Repeat again, because of the fact that the right triangle NQO consists of the small right triangle NSO and the small triangle SQO, it means that the area of the right triangle NQO must be equal to the area of the small triangle NSO plus the area of triangle SQO. So in total, we found out that the area of quadrilateral MNSP plus the area of the right triangle NSO equals to the area of the right triangle NSO plus the area of triangle SQO. So here we have the right triangle NSO on both sides of the equation, so we subtract the right triangle NSO from this equation. So the right triangle NSO will get cancelled from equation 1, and finally we left only with the area of the right triangle MNSP. This equals to the area of triangle SQO. So I did known, according to equation 1, we actually found out that the area of quadrilateral MNSP is equal to the area of triangle SQO. This is according to equation 1. Our mission is to find out the area of the green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of the green shape equals to the area of quadrilateral MPSN plus the area of this shape PQS. Repeat again, the area of the green shape equals to the area of this quadrilateral MPSN plus the area of this shape PSQ. From that agree that the area of the green shape in total equals to the area of quadrilateral MPSN plus the area of shape PQS. But we already found out that the area of quadrilateral MNSP equals to the area of triangle SQO. Therefore, we can substitute the area of quadrilateral, this quadrilateral MPSN by the area of this triangle SQO because they are equal to each other. So we do it now, and we get that the area of the green shape in total is equal to the area of the green shape is equal to the area of quadrilateral MNSP, but the area of quadrilateral MNSP equals to the area of triangle SQP. Therefore, we substitute the area of triangle, we substitute the area of quadrilateral MNSP by the area of triangle SQP. Plus the area of shape PQS. Plus the area of shape PQS. So in total we found out that the area of the green shape equals to the area of this triangle SQP plus the area of this shape PQS. Again, the sum of the areas of those two shapes is equals to the area of the green shape. So the area of triangle SQP plus the area of this shape PQS is equals to the area of the green shape. But what is the area of SQP plus the area of PQS? Actually, the area of SQP plus the area of shape PQS is equals to exactly to the area of sector PQO. Again, the area of sector PQO equals to the area of triangle PQS plus the area of this shape PQS. Therefore, we found out that the area of triangle PQS plus the area of shape, the area of triangle SQP plus the area of shape PQS in total is equals to the area of sector PQO. The area of sector PQO. And what is the area of sector PQO? The area of sector PQO equals to pi r squared, that is the area of the circle, times the angle between the legs of sector PQO, that is 30 degrees, over 360 degrees. And again, I should find out that in total the area of this green shape equals to the area of sector PQO, and the area of this sector PQO equals to pi r squared, that is the area of the circle, times the angle between the legs of sector PQO, that is 30 degrees, over 360 degrees. I repeat again, the area of this sector PQO equals to pi r squared times the angle, the size of the angle between the legs of PQO, of sector PQO, that is 30 degrees, over 360 degrees. You know that the radius of this circle r equals to 5. If r equals to 5, it means that r squared equals to 25. And therefore pi r squared is 25 pi, and 30 degrees over 360 degrees is 1 over 12. So in total we should find out that the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape is equal to 6.545 square units. And this is the answer to the question. Repeat again, we shall find out that the area of this green shape is equal to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape equals to 6.545 square units. Okay, so in the next step, we'll summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the area of this green shape. So in the drawing we have square ABCD. We know that PQ equals to 2, QC equals to 3, and this is angle PQC, that is a right angle. Again, our mission is to find out the area of this green shape. So first of all, we know that ABCD is a square, and therefore all of its sides are equal to each other. We define one side as A, and therefore all the other three sides must be also equal to A units in their lengths. In addition, we know that all the angles inside any square are right angles. So those four angles are all right angles. And we also defined line segment QB as X, and therefore AQ must be equal to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X. In addition, we also defined the size of this angle as alpha. So in the right triangle QCB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third vincent angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. We know that AB is one side of square ABCD, and therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line AB at point Q? We have this angle that is 90 degrees minus alpha, plus this angle that is right angle, plus this missing angle. In total, the sum of those two angles must the sum of those three angles must be equal in total to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q, exactly according to rule 3. So this missing angle must be equal to alpha. In the right triangle QAP, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha according to the third rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I'll copy this right triangle APQ and this right triangle QBC in a new plate, and prove that those two right triangles similar to each other according to angle similarity rule. So actually, those are the two right triangles APQ and QBC that are copied from the original drawing. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the three angles of the right triangle APQ are correspondingly equal to all the three angles of this right triangle QBC, and therefore those two right triangles can go into each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we leave it as it is. QB is X, AQ is A minus X, BC is A, PQ is 2, and QC is 3. So in total, according to equation 1, we can find out that AP over X equals to A minus X over A, and it is also equals to 2/3. Those two sides are equal to each other, therefore we can get the equation 1 from those two sides that are equal to each other. That is to say, so according to equation 1, AP over X equals to, actually those two sides are equal to each other, therefore we can get the equation 1 from those two sides that are equal to each other. So according to equation 1, we can find out that AP over X equals to 2/3. Here we multiply this equation 1 by X, and finally found out that according to equation 1, AP equals to 2/3 times X, 2/3 X. So those two expressions are also equal to each other, so we can get equation 2 from those two expressions that are equal to each other. That is to say, according to equation 2, we shall find out that A minus X over A equals to 2/3. Again, A minus X over A equals to 2/3. Here, of course, multiply this equation 2, and finally found out that 3 times A minus X equals to 2A. Here, we open the brackets on this side of this equation 2, and finally found out that 3A minus 3x equals to 2a. Here we subtracted 2a from this equation 2, and finally found out that 3a minus 2a is a, so a minus 3x equals to 0. Here we added 3x to this equation 2, and finally found out that according to equation 2, a equals to 3x, but according to equation 1, a equals to 2/3 x. In the next step, I copied this right triangle QBC in the new page and implemented the Pythagoras theorem on this right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. Actually, this is the right triangle QBC that is according to the original domain. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9, and it is equal to QB squared. QB is X, therefore QB squared is X squared, plus BC squared. BC is A, therefore BC squared is A squared. So in total, according to equation 3, we shall find out that 9 equals to X squared plus A squared. But according to equation 2, we only found out that A equals to 3x. If A equals to 3x, it means that A squared equals to 3x squared. Therefore, we can substitute A squared in this equation 3 by 3x squared. We did it, and we shall find out that according to this equation 3, 9 equals to x squared plus A squared, and A squared is 3x squared. So in total, we shall find out that according to equation 3, 9 equals to x squared plus 3x squared. 3x squared is 9x squared. So in total, according to equation 3, we shall find out that 9 equals to x squared plus 9x squared. So 9 equals to x squared plus 9x squared is 10x squared. So in total, according to equation 3, we actually found out that 9 equals to 10x squared. Here we divided the equation 3 by 10, and finally found out that x squared equals to 9 over 10. Here we took out of this equation, and finally found out that x equals to the square root of 9, that is 3, over square root of 10. In total, we found out that according to equation 3, x equals to 3 over square root of 10. And we know that a equals to 3x, so a equals to 3, and x is 3 over square root of 10. So in total, a equals to 3 times 3 over square root of 10, 3 times 3 is 9, so in total a equals to 9 over square root of 10. Again, a equals to 9 over square root of 10. Here, a equals to 9 over square root of 10. So here, according to equation 1, we found out that AP equals to 2/3 x. So AP equals to 2/3, and x is 3 over square root of 10. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So in total, we found out that AP equals to 2 over square root of 10. Here, this is 9/7 AP equals to 2 over square root of 10 units in its length. What is the length of PD? PD equals to AD minus AP. repeat again, PD equals to AD minus AP. So PD equals to AD, this is A, minus AP, that is 2 over square root of 10. So PD in total equals to A, that is 9 over square root of 10, minus AP, that is 2 over square root of 10. 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10. So in total we found out that PD equals to 7 over square root of 10. The next step, we join points P and C together by straight line. By joining points P and C, we get two right triangles. Those two right triangles, right triangle PDC and right triangle PQC. Our mission is to find out the green shape. So the area of the green shape must be equal to the sum of those two right triangles that this green shape consists of. So again, the area of the green shape equals to the area of the right triangle PDC plus the area of the right triangle PQC. Why? Because of the fact that the green shape consists of exactly those two right triangles, and therefore the area of the two right triangles must be equal to the area of the green shape. So what is the area of the right triangle PDC? It is equal to the base of the triangle, that is PD, times the height, that is DC, over 2. So again, the area of the right triangle PDC equals to the base, that is PD, times the height, that is DC, over 2. Plus the area of this right triangle PQC. The area of the right triangle PQC equals to the base, that is PQ, times the height, that is QC, over 2. Repeat again, the area of the right triangle PQC equals to the base, that is PQ, times the height, that is QC, over 2. PD is 7 over square root of 10, DC is 9 over square root of 10, divided by 2, plus PQ is 2, times QC, that is 3, divided by 2. So here we have 7 times 9 is 63, square root of 10 times square root of 10 is 10. So in total, this expression equals to 63 over 10 over 2. 63 over 10 over 2, plus 2 times 3 over 2, we have 2 in the numerator, 2 in the numerator, so 2 will get cancelled, and left only with 3. So in total, we found out that the area of the green shape equals to 63 over 10 over 2 plus 3. 63 over 10 over 2 equals to 63 over 10 times 2. 63 over 10 times 2 plus 3. 10 times 2 is 20, so in total, the area of the green shape equals to 63 over 20 plus 3. Here we multiply 3 by 20 and then we divide it by 20 in order to have a common factor with this number. And finally found out that the area of the green shape equals to, here this expression equals to 63, and 20 times 3 is 60 divided by 20. So in total, the area of the green shape equals to 63 plus 60 is 123 over 20. So in total, we found out that the area of this green shape equals to either 123 over 20 square units, or in terms of numbers, the area of this green shape equals to 6.15 square units. We finish with the first question. In the next step, I presented to you the second question and we solved it. In the second question, our mission is to find out the area of this green shape that is located inside quarter circle AOB. So in the drawing we have quarter circle AOB. This is angle AOB, this is the right angle. Those two angles are also right angles. We also know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. So first of all, we join points O and P together by straight line, and join points O and Q together by straight line. So here we implemented rule 20. Complete quickly on rule 20. According to rule 20, in front of equal arcs, there are equal center angles. In the drawing we have a circle, and we also know that arc AB equals to arc CD. According to this rule, all 20, in front those two equal arcs, there are equal center angles. This is to say those two center angles must be also equal to each other because of the fact that they are located in front of those two equal arcs. That is to say the center angle alpha must be equal to the center angle beta. So we can actually implement rule 20 in our drawing. Why? Because in our drawing we know that arc AP equals to arc PQ equals to arc QC. And therefore, according to rule 20, in front of those two three equal arcs, there are three equal central angles. So those three angles, they must be equal to each other because they are located between the equal arcs AP, PQ, and QB. So if one angle, one central angle is x, then the other central angle must be also equal to x because they are equal to each other according to rule 20. So x plus x plus x is 3x from one side, but from the other side we know that this is angle AOB, this is equal to 90 degrees inside. So in total, 3x must be equal to 90 degrees because x plus x plus x, it is exactly equal to angle AOB, this is 90 degrees. So in total, we found out that 3x equals to 90 degrees. Here we divided this equation by 3 and found out that x equals to 30 degrees inside. So the center angle x equals to 30 degrees inside. So in the right triangle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 60 degrees inside. According to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees, that is the sum of the angles in any triangle. Likewise, if you focus on the right triangle NQO, this angle equals to 90 degrees, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size. In the next step, I copied the right triangle NQO and this right triangle MOP in a new page and prove that those two right triangles can go into each other according to angle side angle rule. So actually, those are the two right triangles MPO and NQO that are going from the original drawing. So in the next step, I actually proved that those two right triangles can go into each other according to angle side angle rule. So what those two right triangles can go into each other? First of all, those two angles are both equal to 30 degrees and therefore they are equal to each other. In addition, OP equals to OQ, they are both the area of the circle and therefore they are equal to each other. Again, OP equals to OQ equals to 5, they are both the area of the circle and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So I actually proved that those two angles, and the side that is included between those two angles, that is side PO and this right triangle MPO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is side QO and the right triangle NQO. And therefore, I actually proved that those two right triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles, that is side QO and the right triangle NPO, that are correspondingly equal to those two angles, and the side that is included between those two angles, that is side QO and the right triangle NQO. So those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of the right triangle NPO is equal to the area of the right triangle NQO because of the fact that it can go into each other according to angle side angle rule. Okay, the area, what is the area of the right triangle NPO? This is the right triangle NPO. This right triangle NPO consists of this green quadrilateral MPSN plus this right triangle NSO. And therefore, the area of triangle MPO must be equal to the area of quadrilateral MPSN, this quadrilateral, plus this triangle NSO. And again, the area of triangle MPO equals to the area of quadrilateral MNSP plus the area of the right triangle NSO. And it is equals to the area of triangle NQO. This is triangle NQO. This triangle NQO consists of this right triangle NSO plus this triangle SQO. And therefore, the area of this right triangle NQO must be equal to the area of this small triangle NSO plus the area of this small triangle SQO. Again, the area of triangle NQO must be equal to the area of the small triangle NSO plus the area of triangle SQO, because of the fact that triangle NQO consists of exactly those two small right triangles. Therefore, they must have the same areas. So we have in this equation, we have the area of triangle NSO on both sides of the equation, equation 1. Therefore, we can subtract the area of triangle NSO from both sides. So the area of triangle NSO will get cancelled, and we left only with the area of quadrilateral MNSP is equals to the area of triangle SQO. So actually found out that the area of this quadrilateral MNSP is equals to the area of this right triangle OSQ. Okay, so actually if we define the area of this quadrilateral SA, then the area of this triangle OSQ must be also equal to A, because they have the same areas. Our mission is to find out the area of this green shape. What is the area of this green shape? The area of this green shape equals to the area of the green quadrilateral MPSN plus the area of this shape PQS. But again, the area of the green shape equals to the area of quadrilateral MPSN plus the area of shape PQS. But here, we already found out that the area of quadrilateral MNSP equals to the area of triangle SQO. Those two shapes have the same areas. Therefore, we can substitute the area of this quadrilateral MPSN by the area of this triangle SQO. We did it, and we should found out that the area of the green shape in total equals to the area of quadrilateral MNSP is equal to the area of triangle SQP. Therefore, we substitute the area of quadrilateral MPSN by the area of triangle SQO, and we have also plus the area of shape PQS. So total we should found out that the area of the green shape equals to the area of this triangle SOQ plus the area of this shape PQS. But what is the area of shape PQS plus the area of triangle SQO? The sum of those two areas equals exactly to the area of sector PQO. Again, the area of sector PQO is equals to the area of shape PQS plus the area of this triangle SQO. So the sum of those two areas is equals to the area of sector PQO. And again, the sum of the area of shape PQS plus the area of triangle PQO is equals to the area of sector PQS. It's very easy to see that the area of triangle SQO plus the area of this shape PQS is equals to exactly to the area of sector POQ. And therefore, the sum of the areas of those two shapes is equals to the area of sector POQ. Again, the area of triangle SQO plus the area of shape PQS equals exactly to the area of sector PQO. But what is the area of the sector PQO? The area of sector PQO equals to pi r squared, that is the area of the circle, times the angle between the legs of the circle, that is 30 degrees or 360 degrees. Repeat again, the area of sector PQO equals to pi r squared, that is the area of the circles, times the angle between the legs of the circle, that is 30 degrees over 360 degrees. R is the radius of the circle, that is 5, therefore r squared is 5 squared, that is 25. So pi r squared is 25 pi times 30 degrees over 360 degrees. 30 degrees over 360 degrees is 1 over 12. So in total we shall find out that the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape is equal to 6.545 square units. Okay, thank you very much.